Welcome. In this session, we are going to look at two examples of initial value problems which refer to economics concepts. What makes them perhaps a little bit different is that the initial value, the value of the function, is hidden, in one case more so than the other. So you just have to know how to decode that. Now, first example, they give us the marginal cost function and the fixed cost and ask for the total cost function. The marginal cost is the derivative of the total cost. So I can find the total cost function up to a constant by finding the general antiderivative of the marginal cost function. To avoid confusion, I will use k for the constant of integration. dc over dq is 5 minus 0.002q. An antiderivative for that would be 5q for the term 5. And then minus 0.002 times q squared over 2, this is the power rule. An antiderivative of q power 1 is q to the power 1 plus 1 over 1 plus 1. And then the constant of integration, which I'm going to write as k. So now we have to determine k. For that, I'm going to use the information about fixed costs. Fixed costs are costs which are incurred irrespective of production. Or more precisely, it's the value of the cost function when the output is 0. Let me simplify the antiderivative a little bit. Negative 0.002 over 2 is negative 0.001. And now if I plug in 0 for q, I'm supposed to get 12,000 according to the given information. That allows me to solve for k. 12,000 equals k. So the cost function is 5q minus 0.001q squared plus 12,000. Another example is where they ask you for the demand equation from marginal revenue. Marginal revenue is the derivative of revenue. So by doing antiderivatives, I will get the revenue function. Let's do that first. So an antiderivative of 100 minus 0.2q is 100q minus 0.2q squared over 2. Negative 0.2 over 2 is negative 0.1 plus the constant of integration. In these types of problems, I will use k to avoid any potential confusion with cost functions, even when we're talking about revenue. Next, I have to determine k. So I need to know a value of the revenue function. There is one such value which is always the case, no matter what the situation. If you don't sell anything, you are not going to have any revenue. So when q is 0, r is 0. That's an initial value for all revenue functions, irrespective of the context, at least for in ordinary economics. So you plug in 0 for q and set the resulting revenue to be 0 as well, and then solve for k. In this case, we get k equals 0. So the revenue function is 100q minus 0.1q squared. Now I have to find the demand equation. This is the reverse of what we had to do before. Revenue is P times Q, so P is revenue over Q, or P is R over Q. So I divide the revenue function by Q, and that gives me the demand equation. Of course, I can simplify this one a little bit by dividing each term in the revenue function we found by Q, which gives me 100 minus 0.1q squared. We can factor out q from the numerator and then reduce the fraction, which gives me p equals 100 minus 0.1q. A word of caution. In the two examples we did, the value at 0 was the constant of integration. This will not be the case later on, or even when if you have exponential functions, for example. And it certainly won't be the case in sections 4 and 5 when we start using the method of substitution. So don't fall into the habit of always setting the constant of integration to be the value at 0. That will mess you up with later more complicated problems.